welcome viewers back to this course. So, today we are going to discuss lecture 4. Till now in the lecture 1, 2 and 3 we have discussed about the how we can solve the first order differential equation, the linear and few non-linear equation. Then in the last lecture we have started doing the second order linear differential equation. Then we have defined the linearly independent solution Wronskians. So, today I am going to start with the second linear second order differential equation, and we first will deal with the homogeneous differential equation and then we will go for the non-homogeneous differential equation. So, let us start with the linear equation with constant coefficient. So, I will start with the simple differential equation. So, we have our differential equation. L is the operator, differential operator as we have defined in the last class. So, let us take this one as a d square y over dx square plus b dy by dx plus cy equal to 0. So, in this case what I am doing is I am taking my a, b and c are constants, and this equation is homogeneous because the right hand side function I have taken is equal to 0. So, this differential equation generally we also write Ly is equal to a y double dash plus by dash plus cy equal to 0, because it is very difficult to write each and every time dy by dx. So, we generally for the shortcut we can write this equation as this also. Now, so my a, b, c are constant and this is equal to 0. Now, I want to solve this differential equation as we have also discussed in the last lecture. So, basically if I want to solve this differential equation, I need a function yx, that is the solution of this differential equation, such that if I take the y multiplied by some constant plus the derivative multiplied by some constant plus the second derivative multiplied by constant, I want that should be equal to 0. So, I need a function yx which has yx, y dash x and y double dash x are of same type. Same type means their derivatives I am taking, then also they should be of same time. For example, I start with yx equal to some polynomial. Suppose I take this, that yx is equal to x square. Then I know that its derivative y dash x will be 2x and y double dash x will be 2 only. So, this is a quadratic, this is a linear function and this is 2, a constant function. So, in this case this is of different type. So, in this case this cannot be the solution, of this differential equation. So, what we do is, now I will try to take some another function. So, let us take the another function. So, I take that yx equal to sin x. So, suppose this sin x is the function I want to choose. So, in this case I know that its derivative y dash x will be cos x and y double dash x will be minus sin x. So, in this case if I take the function yx equal to sin x, its second derivative is of similar type, but the first derivative is the cos x. So, if I put this one in this equation, so this is my equation, I call it equation number 1. So, for the second derivative, for the first derivative the cos function will come here in this case. So, if I take the combine all together this function multiplied by some constant, I cannot get the value equal to 0. So, in this case this cannot be also not the solution of this equation, solution of this equation, because if I do not have the first derivative in this equation, then this function is a very good function and I can have the solution of this type. but in this case I have the first derivative also. So, sin x is not the good solution, good approximation or a good function as a solution of this equation. Now, so then I go further and I choose that let us yx is equal to, I choose some exponential function e raised to power lambda x. Then I know that if I take the derivative of this function, it will be e raised to power lambda x, and second derivative of this function is equal to lambda square e raised to power lambda x. So, in this case this function, its first derivative and its second derivative are of similar type, just multiply by some constant, that is a lambda. So, it means that this can be a good choice for the solution of this differential equation. So, let we choose, we start with yx equal to e raised to power lambda x, and then I substitute this in the equation number 1, then I will get that it should satisfy the equation because this is a solution. So, on substitution I will get a should get a, and then the second derivative will be lambda square e raised to power lambda x plus b lambda e raised to power lambda x plus c e raised to power lambda x equal to 0. And then from here we can find, we can take this lambda square plus b lambda plus c together and taking e lambda x outside, then become this one. So, we have also discussed that in the previous lecture, then this function is not equal to 0. So, it cannot be 0. So, we take this quadratic a lambda square plus b lambda plus c equal to 0. This is called the characteristic equation, or the, so this is called characteristic equation, or sometime also we call it auxiliary equation. So, now this is the quadratic equation because we are dealing with the second order linear differential equation. So, it has the roots, because this quadratic equation I can find the roots of this quadratic equation by the methods. We already know that how to find the roots of this one. So, now, so I have this a lambda square plus b lambda plus c equal to 0, and then I know that its roots can be found with the help of minus b, the formula, standard formula, b square minus 4ac by 2a. So, in this case I always go for two roots. So, lambda 1 is minus b plus b square minus 4ac is equal to 2a, and lambda 2 is equal to minus b square minus 4ac by 2a. So, 4ac. So, I am going to have two roots. Now, depends upon that the roots will be real roots, it will be distinct roots, it will be complex roots, it will be repeated roots, everything depends upon this factor b square minus 4ac. So, I will take the case number 1. So, when I take that my b square minus 4ac is positive, it means in this case I will have two roots. So, that will be lambda 1 and lambda 2. So, this will be real roots and distinct, because in this case I will put the value of that one. So, it will be plus and minus. So, it will be distinct roots. So, if these are, they are the distinct root. So, let I have two solution now. So, now let y1x I choose e raised to power lambda 1x, and y2x I choose e raised to power lambda 2x, because these roots are real and distinct. Now, I want, because I know that the the general solution of this differential equation will have two arbitrary constants, and also the y1 and y2x should be linearly independent, only then I can define the general solution of this differential equation. So, now in this case I got these two solutions. So, let us see that what will happen about the Wronskian of y1 and y2x. So, in this case my Wronskian will be E lambda 1x, E lambda 2x, it will be lambda 1 E lambda 1x and lambda 2 e raised to power lambda 2x, as we have discussed the Wronskian in the last class. So, if I go find out the determinant of this one, so it will becomes lambda 2 minus lambda 1, this is lambda 2 minus lambda 1 e raised to power lambda 1 plus lambda 2 x, because this will be multiply minus this one. Now, in this case I know that this part is never 0, and since lambda 1 is not equal to lambda 2, which implies that the Wronskian E lambda 1x and E lambda 2x is never 0. So, if the Wronskian is never 0 for all value of x, which implies that the solutions y1x and y2x are linearly independent. So, if they are the linearly independent, I can define the general solution of the equation number 1, and that will be yx is equal to some constant C1 e raised to power lambda 1x plus C2 e raised to power lambda 2x. So, that is my general solution of the equation number 1. So, this is the case 1, and so if I want to do the example, so let us take one example. So, I start with the differential equation y double dash plus 5y dash plus 4y equal to 0. So, in this case I want to write, because I can write the directly the characteristic equation. So, the characteristic equation is, so I can write directly lambda square plus 5 lambda plus 4 equal to 0. So, from here I will get lambda is equal to minus 4 and minus 1. So, these roots are real roots and they are distinct. So, now I can write the general solution of this differential equation. So, this will be C1 e raised to power minus 4x plus C2 e raised to power minus x, and they will be linearly independent. So, this is the general solution of this differential equation. Now, I will move little bit further, and then I take the case number 2. So, case 2 I take that if b square minus 4ac is negative. So, in this case I will have complex roots, and the complex roots will be that the lambda 1 will be minus b plus iota 4ac minus b square under the root by 2a, and the lambda 2 will be minus b minus iota. So, this iota is a complex number, 4ac minus b square under the root by 2a. Now, in this case we have the two solutions, two roots lambda 1 and lambda 2, and they are complex roots. So, we know that if I want to find out the solution, then my solution will be e raised to power lambda 1 x and e raised to power lambda 2 x. Now, first we have to define that how we can define the exponential function for a complex number, because this is a complex number. So, let us say that I want to define that what is the value of e lambda 1 x. So, e lambda 1 x will be in this case. So, let us take lambda 1. So, this will be e minus b plus iota. So, what I call it, so let us just to make the calculation little bit simple, I will take this as lambda 1 I will make as a alpha plus beta, where my alpha is minus b by 2a and beta is 4ac minus b square under the root 2a. So, this is my alpha beta. Then I wanted to find what is my lambda 1 x. So, it will be alpha plus I beta into x. Now, this is the exponential. So, it will becomes alpha x plus I beta x, and we know that I can separate this one as alpha x into exponential I beta x. Now, this is a real function, it is a real value. Now, what about this one? So, we know that this can be written as E alpha x, and by the formula of the Euler, for the Euler form of the complex numbers, I can define this one as cos beta x plus I sin beta x, because this is the exponential and I know that I can expand this exponential as 1 plus I beta x plus I beta x square by 2 factorial and so on by the exponential series, and then we separate the things. So, this will reduce to this form. So, cos beta x plus I sin beta x. So, from here now what I do, I separate this function as a real part and the complex part. So, in this case I will have E alpha x cos beta x plus I times E alpha x and sin beta x. So, that is my E lambda 1 x. Now, the differential equation we are dealing with, we need that the real valued function as a solution of this equation, but in this case we are getting the complex valued functions as the solution of this differential equation. So, we have to find out that how we can use this complex valued function to find out the real valued solution of the differential equation. Now, so let us call it this as a sum, I will take it as ux and I will call it I sum Vx. Now, this is my y1x, that is equal to E lambda 1x. So, let us put this one in the differential equation 1, because this is the solution of that equation. So, in this case if I substitute this one in equation 1, substituting in equation 1, I will get ux plus I Vx. So, this will be equal to L of y1. So, second double derivative multiply by a, and then b ux plus I Vx first derivative plus c times ux plus I Vx, and that is equal to 0, because this is the solution of the differential equation. So, it should satisfy the differential equation. So, from here if I further simplify this one and take the derivatives, so this will becomes a u double dash x plus I v double dash x plus b u dash x plus I v dash x plus c, and the same ux plus I Vx, that is equal to 0. Now, I separate the real part and the imaginary part. So, from here I will get a u double dash x plus b v dash x plus c, not v, it is a u dash x plus c ux. So, this is the real part plus iota a v double dash x plus b v dash x plus c v x equal to 0. Now, I know that a complex number, a complex function is equal to 0, it means its real part and the imaginary part should be equal to 0. So, from here I will get a u double dash x plus b u dash x plus c u x equal to 0 from here, and putting this imaginary part equal to 0, I will get a v double dash x plus b v dash x plus c v x equal to 0. So, now you can see that from the complex solutions I will get now two real solutions which are satisfying my differential equation, and that is u and v. So, from the if the roots are complex roots, then even from the one of the root, that is lambda 1, we are getting two real valued solution of the differential equation, and that was our purpose, to find out the real valued solution. So, this is the, and so from here I can say that if my lambda e raised to power lambda 1 x was u x plus I v x, it was u x plus I v x, then this is one of the solution and this is another real valued solution of the differential equation. Now, I want to check that there are the two solutions. So, whether these are linearly independent or not, because I want to define the general solution of the differential equation. So, let us check that whether these are the general solution or linearly independent solution or not. So, in this case what I do, now I have e raised to power lambda 1 x. So, that can be written as e alpha plus I beta that we have defined and into x. So, it is e alpha x, and then I have defined cos beta x plus I sin beta x. So, from here I will got e alpha x cos beta x plus I times e alpha x sin beta x. So, what I do now, I choose the two solution. So, y 1 x I choose e, the y 1 I will choose e alpha x into cos beta x. So, this is the first solution I am choosing, and then I choose another solution y 2 x, that is e alpha x alpha x into sin beta x. Now, I want to find their Wronskian. So, this is y 1 and y 2 x. So, this one I am finding out. Now, this e alpha x and e alpha x, these are common. So, I can skip this one from here just to ease the calculation, and I can just check what about this cos beta x and sin beta x, because this is the common. So, I can take the common outside. So, because this is the common function. So, if these two functions are linearly independent, then we are done. So, in this case it will be minus beta sin beta x, and this will be beta cos beta x. So, from here if I take the determinant, so this will become beta cos square beta x plus beta sin square beta x, and this is beta into 1. So, this become beta, and beta is always not equal to 0, because if beta is 0, then we have a real solutions. So, in this case we are considering that we are going to have the complex roots. So, my beta is never equal to 0. So, from here my Wronskian is not equal to 0. So, from that I can say that y 1 x and y 2 x are linearly independent. Now, if I have the linearly independent functions, and that is the solution of the given differential equation. So, from here I can define my general solution, and that will be C1 y1x plus C2 y2x. So, then I can define my general solution for my differential equation. Now, so let us do one example based on this one. So, example, let us take one example, 4 y double dash plus 4 y dash plus 5 y equal to 0. So, this is my second order linear differential equation with constant coefficient. Then from here I can define my characteristic equation. So, characteristic equation will be 4 lambda square plus 4 lambda plus 5 equal to 0. So, in this case if I want to find the roots of this equation, so I will get the roots. So, lambda 1 I am getting minus half plus iota, and lambda 2 I am getting minus half minus iota, because from here I can define my roots minus b minus 4 plus minus b square is 16 minus 4 AC. So, it will be 80 by 2a, it will be 8. So, this will becomes minus 4 plus minus iota. So, it will be 64, so 8 by 8. So, it will be minus half plus iota and minus iota. Now, I get the two complex solutions for the lambda 1 and lambda 2 are the complex numbers. Then from the theory we know that my solution in this case, so my y1 x will be, now my solution is this one. So, my yx solution was e raised to power lambda x. So, from here I will define e raised to power minus half plus iota x, just I will choose only one, lambda 1. So, from here I will get e minus x by 2 into e I x. From here I will get that it becomes e minus x by 2 and e raised to power I x becomes cos x plus I sin x. So, from here I will get e raised to power minus x by 2 cos x plus I times e raised to power minus x by 2 sin x. So, this is my complex function, and from there, so just now we have done that from this one I can find out the two linearly independent solution. So, from here I can directly write my y1 x will be e minus x by 2 cos x, and my another solution y2 x will be e raised to power minus x by 2 sin x. So, in this case there is no need to find out that what is going to happen if we choose lambda 2, the same thing will come again. So, from here I will get two linearly independent solution, and once I get this two linearly independent solution I can write my general solution for the differential equation. So, this will be C1 and e raised to power minus x by 2 cos x plus C2 e raised to power minus x by 2 sin x. So, that will be the general solution of the given differential equation. So, because if I have the general solution, then by giving the initial problem I can find out the value of C1 and C2, and then in that case we will get the unique solution of the given equation. Now, so after doing this one I will go for the case number 3. So, this one we are doing only for the homogeneous case with the constant coefficients. So, in the case number 3 it may happen that b square minus 4ac, that is in the when we find out the roots of the quadratic equation. So, this becomes equal to 0. So, in that case what will happen, my lambda 1 will be minus b by 2a and my lambda 2 will be minus b by 2a. So, in this case the roots are real and repeated. Now, if I write the solution corresponding to these two, then I can write my y1x is equal to e raised to power minus b by 2ax and my y2x will be e raised to power minus b by 2ax. But the problem comes with this one, that this solution and these solutions are linearly dependent. But to find out the general solution of the equation, I need two linearly independent solutions. So, but in this case we are getting only linearly dependent. So, for what we will do that, for this one I will find out the, so with the help of this I want to define, so with the help of the one solution, because one solution is known to me, I want to find another linearly independent solution of the equation 1, whatever the equation I have started with. So, I want another linearly independent, because in this case I can choose only one solution and the another solution I want to find. So, this another solution we can find with the help of very renowned methods. So, that is called the reduction of the order of the method. So, this is the reduction of the order of the equation. So, how I will do that? So, in this case I will write that the let I will get another solution y2x is equal to, suppose I have some vx and then y1x, I choose this one. So, y1x I will choose like this one and v1x. So, vx is a function of x and I do not know that what is the value of the vx. So, and this y2x is the solution of the equation number 1. Now, so before that I just take the derivatives of this one. So, my y2 dash will be, so taking the product rule, it will becomes v dash, just I skip the writing x and again, but it understood a function of x. So, I will write v dash y1 plus v y1 dash. So, this is the first derivative, and the second derivative will be again v dash y1 plus v dash y1 dash plus v dash y1 dash plus v y1 double dash. So, this is the second derivative we have taken. So, from here if I choose substitute this solution in the equation 1, then I will get L of y2 x will become a. So, now I am writing not as a function of x, just for the, so that the calculation will be easier. So, I am writing v into y1, no just this will become, because I have to second derivative. So, second derivative will be v double dash y1 plus, now this into this. So, it will be 2 times. So, this will be 2 times v dash y1 dash plus v y1 double dash, now plus b. So, b I will, so it will be v dash y1 plus v y1 dash plus c, and this will be v y1, and because this is a solution, it satisfies the differential equation. So, this is equal to 0. Now, from here I will take the, I will separate the, I will separate the all the quantities related to y1. So, if I separate this one and choose the y1 as a common, so I will get a v double dash plus b v dash plus, now so I will just keep this one here, this one I will, because this will be used. No, so I will now what I do is I will write a v double dash y1 plus b v dash y1 plus, now this is 2 times I am taking here and this is y1 dash. So, from here I can write that v I am taking common. So, from here I can write a y1 double dash plus b y1 dash plus c y1 plus, and then this I have already chosen, this I have already taken from here, plus 2 times a v dash y1 dash equal to 0. So, this will become this. So, this is the, we have separated the given equation to this form. And now, what about this one? So, this one I know that this is the equation we have started with, and y1 was the solution of that equation. So, its value should be equal to 0. So, from here this reduced to a v1 dash y1 plus b v dash y1 plus 2a y1 dash v dash equal to 0. And from here I can write this equation as v double dash plus, because I can divide the whole equation by a y1. So, it will be again b by a v dash plus 2 y 2 y1 dash over y1, and a will cancel out, v dash equal to 0. So, from here I will further write it like this one. So, it will reduce to 2 times y1 dash over y1 plus b over a y dash equal to 0. So, this equation, if you see that this equation is a first order equation for the y dash, and this first order equation I can solve this, because we already know that how to solve this first order equation. So, the first order equation, this equation I can solve. So, from here my v dash will become e raised to power. So, I will take the constant of integration c e raised to power minus 2 y dash over y1 y dash plus b over a x, and this is the constant of integration. Dx. So, this is the integration I am taking, because just I will take on the right hand side and then the separating of variables, I can find out the solution of this one. So, from here, and this c is the constant of integration. So, from here my y dash will be c e raised to power minus integration b over a dx into, I just y1 over 2 y1 dash dx. So, separating this one. From here I can solve further. So, what it will becomes? It will become e raised to power minus bx over a, and this will becomes e raised to power, and this is the function and its derivative, so it will be e log y1 and then the square. So, from here further I can write this one as c e raised to power minus bx by a, and then it becomes e minus, from this one I can write directly that this will be reduced to, because exponential and the minus of log this one, so this I can write as y1 square, because this I can take as this one. So, from here further I can write this as c e raised to power minus bx by a by y1 square. So, this is my v dash. Now, if I further solve this one, from here I will get v dash is equal to c e minus bx by a by y1 square. Then what was my y1 square? My y1 square was e minus bx by a, and what was my y1? y1, if you see the y1, my y1 was this one, e raised to power this. So, this is my y1. So, from here if you see, my y1 was e raised to power minus bx by 2a and the squaring of this one. So, if I take this one, it becomes c e raised to power minus bx by a, and then taking the square of this, so it again becomes bx by a, because 2 will cancel out from this and this will cancel out, and you will get the constant of integration, that is c. So, from here I will get v dash is equal to c. Now, I will get v dash equal to c, and the constant integration is this one. From here I will take the integration both side with respect to x, and I will get vx will be integration cx. So, just for the simplicity I will choose c is equal to 1. So, from here, because I need only one solution, this is a class of solution and I need only one solution for this one. So, I choose c is equal to 1. So, from here I can define that my Vx will be x. So, if I choose Vx equal to x, then I can now define, from here I can define that my y2x will be x into y1x, and y1x was, so it will be x e raised to power minus bx by 2a. And you can also check that y1x and y2x are linearly independent. So, this will be linearly independent, that you can just do yourself, it is very easy to check. So, from here now I get y1x I know, and y2x is this one. So, from here I can define my general solution. So, the general solution I can write as yx is equal to c1 e raised to power minus bx by 2a plus c2 x into e raised to power minus bx by 2a, and from here I can write this one as c1 into x c2 e raised to power minus bx by 2a. So, that is my general solution for this differential equation, and these are the case when the roots are repeated. Now, so let us take one example based on this one. So, let us solve this one. I have a differential equation y double dash plus 4y dash plus 4y equal to 0. So, in this case I have my characteristic equation will be lambda square plus 4 lambda plus 4 equal to 0, and here I will say that this becomes whole square equal to 0. So, from here my lambda is minus 2 minus 2. So, now this is the roots which are real and repeated. So, from here if I want to write my solution yx, so yx will be c1 plus x c2 e raised to power minus 2x. So, this is my general solution for this differential equation. So, this is the 3 types of cases that depends upon the roots of the quadratic equation, and the quadratic equation is the characteristic equation that is corresponding to the differential equation we are solving. So, these are the 3 cases, and based on these cases we can find the general solution for the homogeneous equation. Now, so after solving the homogeneous differential equation, now we will start with the non-homogeneous. Non-homogeneous equation with constant coefficients. So, in this case I have, so let us define the equation. So, this is my Ly. So, that is I am writing a y dash plus b y dash plus c y equal to some function f x. So, in this case my f x is not equal to 0. So, this function I am defining, and this function is not equal to 0. So, this become a non-homogeneous second order linear differential equation, where my a, b and c are constants. Now, how we solve this type of differential equation, the non-homogeneous differential equation, because this is again a second order differential equation. So, for this differential equation if I want to write the general solution, so that general solution should contain 2 arbitrary constant again to find out the general solution. So, for this one I will just define one theorem that let y1x and y2x be 2 linearly independent solutions of the corresponding homogeneous equation. So, that is I can write as a y dash plus b y dash plus c y equal to 0. So, this is the corresponding homogeneous equation attached to this non-homogeneous. So, let y1 and y. So, in this case what you do, first we solve the homogeneous case, and from that homogeneous case I will get the 2 solutions, and that we know how to solve this one. So, this will be y1x and y2x, then and let I will call it ypx. Let ypx be any particular solution of the, so let us give it name, so I call it 2. So, let ypx be any particular solution of the equation 2, then the general solution of equation 2 can be written as, so I can write the general solution, that is yx. So, we call it, actually we split this one into 2 parts. So, I will call it, first one is ycx and then ypx. So, what is the YCX? This is the solution and it is called the complementary solution. So, these solutions I will call it complementary solution, or I can say that the solution of the corresponding homogeneous equation. So, the now put right hand side equal to 0, and whatever the equation we get, if we solve that one. So, this is the complementary solution and the solution corresponding to the homogeneous equation. So, from here I can write that my Yx will be, so this my Yx will be C1 Y1x plus C2 Y2x plus Ypx, and that will be my general solution. So, in this case I have two arbitrary constant that should be there in the solution of the second order differential equation, and this is the particular solution. So, this is the same way we used to solve the system of linear equations, the algebraic equation. So, in the system of non-homogeneous algebraic equation, we always first find the solution corresponding to the homogeneous linear system, and then we find the solution for the corresponding non-homogeneous system, and then we add together. So, this is the general solution of the equation 2, where same as C1 and C2 are arbitrary constants. So, now I want to find out, because this C1 Y1x plus C2 Y2x, the complementary solution is very easy to find now, because we already know the methods to find out, but how to find the Vpx, that is the main challenge. So, and the Vpx is also based on that what is the value of my function, whether my function on the right hand side is a quadratic, is a polynomial, or whether my function on the right side is the exponential function or a trigonometric function or any function. So, based on that which type of the function fx on the right hand side we have, we will go for the different methods to solve the differential equation to find out my particular solution, that is Ypx. So, this will be, we start, I will go for different methods. So, in this case we choose for, there is a method that is called operator methods for finding particular solution, and that is Ypx of equation 2. So, this is, I am going to use operator method. There is another method also, but in this course we are going to do with the operator methods for finding particular solution Ypx of the equation number 2. Now, we already know that the equation 2 can be written as, so this is Ly I have. So, this I can write as a y double dash plus b y dash plus c y equal to fx, which can also be written as Ly is equal to a d square plus b d plus c y, y means the function of x. So, this is Yx is equal to fx, where my d is a derivative. So, this is called differential operator. So, I will make use of this differential equation. I can write this differential equation further, and this becomes Ly is equal to, so this if you see that it is a d square plus b d plus c. So, it is some function of d. So, I can write this as a f d y x, and that is equal to f x. So, this is my differential equation now, where FD is the differential operator. From here, now if I want to solve this one, I define Yx is equal to Fd inverse function Fx. So from here, I can solve this one. So that becomes my Ypx will be Fd inverse Fx. So this is my particular solution. Now the problem is that how to find this inverse of my Fd. So this we will discuss in the next lecture. Thank you very much.